Hey, William. Okay, so for the exam 2, so I printed out, or I posted, did you all see the list of the definitions and theorems that you need to know? Okay. And so, so that list is there online, and there are so many that it's like, do I tell you theorem 2.7? Say that, I don't know. It's just, I don't know. Anyway, so I guess know the theorems and their statements, and then know the definitions. And then for proofs, so the theorems that you need to know, the proofs, theorems whose proofs you should know. How about let's say those. So there's theorems. Okay, so let me read here. So in chapter 1, in the last section of chapter 1, theorem 1.7. So theorem 1.7 was the one that said that every integer is a product of primes. And so you can prove that one of two ways. You can use the well-ordering axiom. Or you could do it with induction. Well, actually you have to do strong induction. And we did both of those in class, but if you're not sure what I'm talking about, just let me know and I can talk through those proofs with you, okay? So the well-ordering one is the one that's in the textbook, and then we did it the same proof with, or the same theorem we proved with strong induction also in class. Okay, so that's the main one from that section. And it's not long, like none of these proofs are that long. So that one, and then theorem 2.1 is a big one because it shows that basically it says that congruence mod n is an equivalence relation. So for that proof, you're just checking the 3 conditions for equivalence relation for congruence mod n. So that's not very long either, because it's just like all those other equivalence proofs. So that's theorem 2.1. And then the other proof that I want you to know is the one we're going to do today, theorem 2.8. And this one is kind of long because it has 3 statements and you're trying to prove that they're equivalent to one another. And so, so you should know the whole proof, but like, I'd probably just ask you to reproduce part of it. So, so those are the 3 proofs that you need to know. And so I may or may not put all 3 of those on there, but each part of these is short enough. I think it should be fine. So those 3 theorems know the proofs, and then the other theorems just know the statements of them and be able to use them. Okay. So you should start making, if you haven't made your flashcards yet, you should start making your flashcards for your definitions and your theorems, and then the proofs of these theorems. So questions about that?
Last time you gave us like a list of which definitions, is it just all of them?
Yeah. Yeah. I mean, I think last time it was all of them. We've just done a lot. We've done a lot in the last bit of material has been a lot. So anyway, so yeah. So again, that makes it challenging. So would you prefer to do the memory work part of the exam? So if I'm going to do the main exam on Wednesday, then I can give you like 30 minutes to work on the memory part on Monday, or would you rather do it on Friday? Zach?
I vote Monday.
You vote Monday? Okay, what do you all think? I always hate putting an exam on Monday because I feel like it's gonna be too, like, you're gonna forget about it and then it's like, oh crap, it's Monday morning and I have this thing. Hopefully you won't forget about it. I mean, y'all are juniors, seniors.
You're talking about like the definitions and stuff.
Yeah, yeah, so I'll probably do, and some of this proof stuff. So, because last time I want to give you an equivalent amount of time that Dr. Ortman's students have, because they have a 75-minute class. And so our class is 50 minutes. So I was going to give you an extra 25 minutes on one of those days to do some of this memory work.
Do we need, we'll work through everything today, so we don't need time on Monday to like finish up anything.
Oh, no, it's not this coming Monday.
Oh, the next.
Yeah, it'll be a week. Yeah. Yes, yeah, I think that would be a little crazy to have you memorize theorem 2.8 if you haven't even done it yet. So you'll have over a week on that. So Monday, so we'll do that. We'll do the memory part on the Monday before the exam. Okay. And that's all we'll do on that day. And we won't have any homework due that week. So you'll kind of get a little bit of a break on that end. Okay. So so that's the plan. Okay. And so, yeah, so let's get going for today then. So go ahead and pull out your worksheet from Wednesday. We hadn't finished it quite yet. Okay, so do you want me to put the actual date, the Monday before the exam? Okay. Let me look at my calendar and see where we are. Okay, so the exam is going to be on the 27th. Okay, so on Monday, October 25th, we're going to do exam part 1 with just memory stuff. And then Wednesday, October 27th, then we'll do exam part 2.
That memory is like all of the definitions and everything.
Yeah, I mean, I'm not going to ask you to write down all of them, but
Right.
yeah, a selection of them. Yeah, will be proofs.
So the proofs you want us to memorize are gonna be in part 2 or part 1? Or-
There may be some on each. Yeah. Mhm. Or there may be something on exam part 2 that's similar to one of the other proofs you memorize, you know, so maybe like a variation on that or something. So, yeah. Okay. All right, so so equation solving. So we're looking at this equation. So if you had something like this, and we wanted to solve something like this in Z, okay, how would we solve this in Z? You can think back to what you did in algebra in high school, right? How would we solve something like this?
Just like, if they multiply to 0, one of them is 0.
Yeah, so if they multiply to 0, one of them is 0. So x equals 3. Well, sorry, x minus 3 equals 0. So it's this splits into 2 equations. So I get x minus 3 equals 0. And I get x minus 4 equals 0. So that gives me x equals 3 and x equals 4. Right, so that's how we would solve that in Z, right? And so what did we use to go from here to here? What we used is something called the zero product property. In Z, and actually it's in R, if we wanted to be. So this property holds in R as well. And that's kind of what you've been using and what you used in algebra. So the zero product property says that if A times B equals 0 for A, B, and Z, then A equals 0 for B equals 0. So that's the zero product property. And that was what we used to solve these kinds of quadratic equations. Okay. So let's talk about the same equation in Z mod 5. So we have x minus 3 times x minus 4 equals 0, and we're in Z mod 5. So for this one, what I want you to do is plug in, there are only 5 elements in Z mod 5. Plug in every element of Z mod 5 and see which ones work and which ones don't. Okay, so solve that equation in Z mod 5. And then the next one is solve that equation in Z mod 8. And you're just going to do that by checking all the elements in Z mod 8 and seeing which ones work and which ones don't. And y'all can work together on this. So you can divvy up the responsibilities there among your group. And I did put in a multiplication table for Z mod 8 if that helps you. William, do you see that? Do you still have your worksheet from Wednesday?
I do.
Okay.
I guess, I mean, like you could do. I think this is wrong. Actually, the same number. Do 6 and 8.
So like mod 8 equals what?
Well, no, in mod 5, you can still plug in, like 6, it's just 6, oh, I'm sorry, not 6. You can plug in 8, and it's congruent with resources.
So to be clear, this is what we really mean here. Right, so we're looking for our congruence class, right, solution. So since we're working in Z mod 5, we're really talking about congruence classes. So but I think what you'll find is as we start working with these sets, or they're going to be rings. We're about to say that they're rings, but as we work with these, we're going to end up dropping the brackets just because they're too tedious. So.
Seven months is 4, 6 months 4 is 2, and 4 is 2 is 0. Yeah, I don't think so, because like, is it, you can just add the mod in the sentence. So I'm for 7 here, you end up with 4, 2, and then 4 and 4 also. That's equal 6. No, 6 minus 4. Yeah. Oh, that makes more sense. I was like,
It's just feeling like the useful. So in text marks. For. And then next one, what was to do. I don't know. Was that just because of the stats then? I think? Yeah. I mean, like. First one would be. Let's see all this.
Okay, what did you all get in ZMod 5? Did you have any solutions that worked? What were the solutions that worked in ZMod 5? Just 3 and 4? Okay. So those are the only things that worked in ZMod 5? Okay. What about in ZMod 8? Colin?
I had in ZMod 5 at 8, and also, wait, 8 and 9 were. Wait, what am I saying? 8.
8 worked and 9 worked?
Wait, hang on. 3 plus 5 is 8. 4 plus 5 is 9. Yeah.
Yes, okay. But this is actually equivalent to that, and that's
Yeah.
equivalent to that. So those are not new solutions. So, yeah. So since we're talking about, sorry, did those arrows make it confusing? So yeah, so in other words, I'm saying that the equivalence class of 8 is equal to the equivalence class of 3. So those are not new solutions.
Okay, so like the 8, so we have the 8 is equivalent to 3. If you plug 8 into that equation and evaluate force before you do the congruence, you get a non-zero times a non-zero equals 0. So like, what do we mean when we talk about like, does the order matter in which you like do an equation? And
Well,
then apply
let's
congruence, or-
plug 8 into here. So if we had 8 minus 3 times 8 minus 4. Well, what is this? This is 5. But 5 is 0. So that is a 0.
Right.
Right? So we get 5 times 4. So really we should have brackets, or, I mean, we're in ZMod 5, so all of these are congruence classes. We have the congruence class of 5 times the congruence class of 4. Well, the congruence class of 5 is 0.
Okay.
Right? Yeah, so we don't end up with a non-zero thing times a non-zero thing equals 0.
Okay.
No, good question. Well, and it comes down to how we've been like kind of lax with like whether we're talking about a congruence class or an element in Z, you know?
Right.
And so, so we do have ways of going back and forth between those two things, right? So, so I could say like A is equal to B in Z mod N. And that is equivalent to saying that A is congruent to B mod N, where A and B are in Z. Okay? So I can talk about things in terms of equivalence classes in Z mod N. I can also say similar things as numbers in Z mod N. Okay. And then this means that A minus B is equal to NK for some K and Z. Right. So, so we're kind of, well, sometimes we'll talk about things in this way and sometimes we'll talk about things in that way. Okay. And so, to try to be clear, I'll try to put brackets on everything today when I'm talking about this space and not put brackets when I'm talking about that space. Okay. So, so I'm going to try to be super clear today. So anyway, oh, sorry, William, you didn't see any of that. Oh my gosh, I'm failing. Okay. All right. So in Z mod 8, what were the solutions you found? Three and four also work. Anything else? No other X values? Did you plug in all the X values? Nothing else worked? Okay, I didn't actually work this one out, but
Well, you could do like X minus 3 equals to like 4. And then X minus 4 equals to 2.
yeah,
4 times 3 is 7.
X minus 3 equals 4 and X minus 4 equals 2. Then that gives you X equals 7. Okay, we're doing this actually. And now why 4 and 2? Why did you pick 4 and 2 here?
Says if you multiply it to 0.
Yeah, so in mod 8, we have something multiplied by something. It doesn't mean that each of those things are 0, right? So 4 multiplied by 2 gives us 0 in mod 8, right? So we could have X equals 7, or we could have X equals 6, right? And we also have that, let's see, we have a lot of 0 divides, 4 times 6 and 6 times 4. So we could have X minus 3 equals 4 and X minus 4 equals 6. Does that give us something different? That's 10, which is 2, right? We get 7 and 2. Or some other solutions.
You have to put those in like the order pair because they only work.
They only work when they are,
Yeah, that has to be the same.
Well, they don't work, as long as one of them 0, it's 0.
But they have to like multiply by each other.
That is true.
Oh, yeah, but then X
Yeah, that
equals
makes
7, right?
Yeah, because if you plug in X equals 7, it equals 12, not 0. So it'd be 4.
right, so if you plug in X equals 7. And, oh, I see what you're
Yeah.
saying.
Yeah, 6 doesn't work either for the same reason.
Yeah, so you would have to have, it would have to be like X minus 3, Y minus 3 to do, or Y minus 4, right, to get that. Colin?
The way I thought about the sanity check is the difference between those two terms is 1. So if that has any zeros other than 3 and 4, you have to have a 0.
It would
right
have to
next
be like X minus 3, X minus 5, right? Would give us something, because like, if. So you're saying the difference in the 3 and 4 is 1, but when I look at the 0 divisors, I have 2 and 4, and then I have 4 and 6, and they're 2 apart from one another, right?
So it's
So
seven.
to craft a polynomial like this that would have 0 divisors, I would have to have the difference in those two be 2.
Yeah, because that 7 would work. Because
The 7 would work?
4 and 2.
Yeah.
Yeah. Okay, so, all right. So I should have used this polynomial. That's the moral of my story there.
73, 5, and 7.
Right, yeah. So in other words, because I know that Z mod 8 has 0 divisors, right? Because Z mod 8 has 0 divisors, it's possible to construct a polynomial that has more solutions than we expect, right? Is kind of the point. Okay. That was my whole point. This whole thing. Yeah, and so the 0 product property, in other words, the 0 product property does not hold in Z mod 8. So we have to be careful because Z mod 8 has 0 divisors. Okay. So the reason that the 0 product property holds in Z is that Z has no 0 divisors, which we'll learn soon, right? Well, we're going to talk more about rings very soon, but this has no 0 divisors. And so I can use that property to just solve it. And in Z mod 5, does Z mod 5 have any 0 divisors? It doesn't, because that's a prime, right? And so we had talked about that if that P was a prime, that there would not be any 0 divisors, and every non-zero element is a unit. And so that's actually theorem 2.9, which we're going to state today. Yeah, hopefully.
I'm sorry.
Go ahead.
So what I was gonna ask if this is actually what's going on, I was just trying to think about, on this thing where we had the difference between x minus 3 and x minus 4 was 1. I was looking at the multiplication table. And so if you had a solution, it would have to be right next to the main diagonal. There would have to be a 0, like just to the side of it, where the difference between the row and the column is 1. And the only time that happens is at 0, 1, and 1, 0. Is that the same thing as saying there's only that one solution, or those two solutions?
Yes. So you're saying the difference in the 3 and 4 is 1?
Yeah.
Yeah, so you would need to have a set of 0 divisors that when you multiply them together, but the 0 divisors have a difference of 1 between them.
Yeah, so the row and column would be like 1 apart, so they'd be right next to the main diagonal, but not wrong.
Yes, like 4 and 3, in other words.
Yeah,
But they're on the main diagonal. Oh, I guess it depends on what you mean by the main diagonal.
I mean like matrix style diagonal, I guess.
Yeah, okay, hang on. So sorry, I can't see here. So 4 and, oh, that diagonal. Okay, yes. Yes, I see what you mean now. Mhm. Yeah, that's what we're looking for then. We're looking for a 0 divisor that's off, just 1 off of the main diagonal. Yeah, so if you didn't follow that, that's fine. But that's just another way of thinking about it, but looking at the multiplication table. Okay, so sorry that flopped, but anyway, we were able to construct an example that works, so there you go. But yeah, so I need to make a note to myself to put that on my worksheet instead of this other one that I have. So maybe next time if I ever teach this course again, I can use that. Okay, so that's all for that. So let's go on to theorem 2.8 today. So we need to get this proof done. And actually I didn't take roll. Let's see who's missing. We're just missing Brian and Williams online. All right. So it may seem like we haven't done very much, but you all have done so much exploring on your own. You've like conjectured every theorem that we've that's in this section. So, so you all really have a nice hold on things, even if you may not feel like it. But the thing I'm going to do as I write this proof is I'm going to be really careful to use brackets when I mean it and not when I don't. Okay, so All right, so here's the theorem, 2.8. Okay, so let's do this. So I'll give you a chance to catch up on writing, but I'll read this out loud. If p greater than 1 is an integer, then the following are equivalent. The first thing is p is prime. The second thing says for any non-zero element in Z mod p, the equation ax equal 1 has a solution in Z mod p. In other words, the element, any non-zero element has a multiplicative inverse, right? And then this says whenever b times c equals 0 in Z mod p, then b equals 0 or c equals 0. So in other words, it has no zero divisors. Okay. So let's write that. So this is, I'll write it in green. So that's what that says. And then this says every non-zero element has a multiplicative inverse. So that's how we've been talking about things in class. Okay, so you believe it? You've done enough examples to believe it, I bet, right? Yeah. Now we just have to prove that it's true. Now, this is an interesting statement. You haven't seen a statement like this before, have you? The following are equivalent, and you have 3 things. So this is a new kind of statement. And so the method for proving this kind of statement is that we'll prove 1 implies 2, then we'll prove 2 implies 3, then we'll prove 3 implies 1, and then that will get everything, right? And so that will get both directions of all the if and only ifs for all of that by doing it that way. So we're going to prove 1 implies 2, 2 implies 3, and 3 implies 1. So that's going to be our method of proving this, okay? So yeah, so let's go. So if p is prime, so let's remind ourselves what we have if p is prime. So we have a couple of things. So if p is prime, we have the definition. If d divides p, then d equals plus or minus 1 or plus or minus p. So that's the definition of prime. We also have theorem 1.5, which theorem 1.5 says that p is prime if and only if p has the condition that if p divides bc, then p divides b or p divides c. Okay, so if you know that you have a prime number, you have these 2 things in your tool belt, right? Or if you're trying to prove something is prime, you have these two tools in your tool belt, right? So if you're trying to prove something is prime, you can either say, okay, let's say I have a divisor and try to prove that divisor is those things. Or you could say, okay, let's assume that P divides some BC and then try to prove that P divides B or P divides C, okay? So those are kind of the things we have in our tool belt if we know P is prime. Okay. So I wanted to remind you of those things. Okay, so let's do the first part. Okay, so for the first part, we'll do that 1 implies 2. So we're going to assume that P is prime. And so we're going to assume 1, and then we want to prove number 2. So if I want to prove that, I need to choose some non-zero element of Z mod P, right? An arbitrary non-zero element of Z mod P. And choose A not equal to 0 in Z mod P. So how can we make traction on this? Well, I know that A is some non-zero element of Z mod P. So I can write it in terms of like elements in Z and use the mod and stuff. So if A we know that A is not congruent to 0 mod P. And now this A and that 0 are just integers, regular old integers. Right? So I've translated back into integers. So what does that mean? So if A is not congruent to 0 mod P, what does that mean? Well, that means P does not divide A. Right? Because what does it mean to be congruent to 0? If A were congruent to 0, that means that A minus 0 is equal to PK, right? So that means that P divides A, right? But if A is not congruent to 0, that means that is not true. So P does not divide A, right? So P does not divide A. Okay, so that means the GCD of A and P okay. So let D be the GCD of A and P. Then D divides A and D divides P, right? Well, if D divides P, what do we know? So plus or minus 1 or plus or minus P. Well, it should be only the positive because it's the GCD, right? So D is equal to 1 or P. But if D equals P, then P divides A. Right? But that's a contradiction. So D must equal 1. So the GCD of A and P equals 1. Now, if I have the GCD equal to 1, what does that give me by theorem, linear combination theorem? They're co-prime, yes, but can I write, how can I write A? So there exists a UV in Z such that AU plus BV equals 1. Okay, where are we going? We're trying to get that this equation has a solution in Z mod P, right? Okay, so we're getting closer because now I have A times something and there's a 1 there, right? So I'm getting there, we're getting there. Okay, so we have AU plus, oh, whoops. AU plus PV, not BV. I don't know where B came from. Okay. Oh my gosh, we're not gonna finish this group today. Okay. So let's rearrange. Because I want to get A times something equals 1 is where I want to go, right? So that tells me that AU minus 1 equals P times negative P. I just moved it around a little bit. So what does that mean by definition of mod? That means that AU is congruent to 1 mod P. Right? So AU is congruent to 1 mod P. Agreed? Yeah. Okay, so that tells me by theorem, the one that allows me to go back and forth between that and the, okay, what theorem is that?
1.5, I think. Or no, not 1.5, that's.
No, it's 2 point something. 2.3, yeah. By theorem 2.3, we have that AU equals 1. So AU equals 1 by theorem, the one that lets us break it up. What theorem is that? Some other theorem. Oh, it's definition. It's a definition by definition. So what have I done? Did I finish? Okay, what I'm trying to show is that any non-zero element of Z mod P. So I started with a non-zero element of Z mod P. And I need to show that this equation has a solution in Z mod P. Does this equation have a solution? What's the solution? X equal U. Yeah. Yeah. So the solution, so the equation A x equal 1 has the solution has, okay, maybe that's not the only solution.
What's the class?
X equal. Okay, so I proved that 1 implies 2. Okay. That one was kind of a lot. That was kind of a lot. It pulled from lots of different places. So that was a lot. Okay. Should we stop? It's Friday. Let's stop. So Monday we'll finish 2 implies 3 and 3 implies 1. And but you need a brain break for now, I think, after that. That was a lot. So we'll finish that. You can, if you want to read ahead in the book, you can read it in the book, and that way you'll be ready for Monday. Okay.